SNA CLAW 3270. Mainframe task automation.
Okay, so I want you to picture this. You're staring at a completely black screen, and there's this glowing green text from, I don't know, the 1980s.
Oh, classic.
Right. But instead of having to type out these cryptic, ancient codes, you are commanding it using just modern, everyday English.
Which sounds like science fiction, honestly.
It really does.
Yeah.
But we're looking at a fascinating GitHub project today by a developer who goes by Jim Pames, and it's called SNA CLAW 270.
Yeah, the CLAW. And what's wild about this is the mission behind it. It's built entirely in pure Python, and it acts as this, well, basically a universal translator.
Right.
It bridges the gap between modern natural language processing and these incredibly old legacy IBM 3270 mainframe systems.
Which is just a thrilling concept to unpack. I mean, we're not just doing a dry code review here. This is literally retro tech colliding with modern automation.
Exactly. And to really get what makes it so special, we have to talk about what it isn't. The creator puts a massive disclaimer right up front.
Oh yeah, the not an emulator thing.
Right. It is explicitly not a 3270 emulator. Jim Pames calls it an automation substrate.
An automation substrate, which sounds a bit heavy, but I was thinking about a good way to picture this.
Oh, for it.
So a standard emulator, right? It's like someone handing you a vintage steering wheel and pedals. You still have to drive the old car yourself.
Yeah, you're doing all the manual labor.
Right. But SNA CLAW 3270, the substrate, it's more like a chauffeur. The chauffeur already knows exactly how to drive the vintage car, all the weird quirks of the clutch, and is just sitting there waiting for you to tell them the destination.
That is a perfect analogy, because historically, the way people drove those vintage cars, the way they automated these mainframes, was an absolute nightmare.
The dreaded screen scraping.
Exactly. It'd spin up a visual emulator, paint the green text on the black background, and write a script to look at specific pixel coordinates.
Which breaks if literally anything changes.
Oh, instantly. A sysadmin adds a single line at the top of the screen saying, server maintenance at midnight, and suddenly all your menu options shift down one line.
And your bot clicks the wrong thing, and a critical banking process fails.
Right, because you're trying to interact with the picture of a machine, not the machine itself. But the CLAW abandons that visual layer completely.
Okay, so how does it actually talk to the mainframe then, if it's not looking at the screen?
It natively participates in the 3270 protocol using IBM's TNZ library.
Okay, TNZ.
Yeah, so instead of looking at pixels, it parses the underlying data stream. It understands the structural reality of the mainframe.
Well, let's talk about that structure, because 32270 terminals operate really differently from other old tech, right? Like they aren't sending every single keystroke over the network one by one.
Oh, no, not at all. They are block mode terminals. So the mainframe basically sends down a mathematical blueprint of a form.
Yep.
It's like the mainframe saying, hey, I'm defining an input field at row 12, column 20. It's exactly 8 characters long, and you cannot overwrite it.
And then the user types locally, fixing their typos, and the mainframe has no idea until they hit enter.
Right. An attention identifier key like enter or F1. Then it packages the whole block up and sends it. And the CLAW operates right at that architectural level.
So it's reading those invisible field definitions directly. It knows mathematically where the boundaries are.
Exactly. And that brings us to how it actually drives the mainframe, which relies on a really specific configuration file.
Yes, the skills catalog, the skills.ini file. I was looking through the debug logs, and it's fascinating how atomized these skills are.
They're very granular.
Yeah, like out of the box, there are just 5 default skills. You've got navigating the Cerberus gate, signing onto the system called CSP.
Signing off, selecting a menu, and listing files.
Right, and you mentioned the substrate concept earlier. These aren't big, messy scripts.
Yeah.
They're defined as small, gated, replayable units of work.
That's the key. And the engine strictly enforces 2 things for every single skill: preconditions and postconditions.
Okay, wait, I actually have to push back on this a little.
Oh.
So, looking at the debug trace, the proof.txt file, I saw how it checks the precondition for that MUSICSP sign-on skill.
Right, to make sure it's on the right screen.
Yeah, but the log shows it looking for this massive text banner that says multi-user system for interactive computing system product. If it's literally just scanning for a specific string of text to prove it's in the right place, how is that any different from the dumb screen scraping we were just complaining about?
I mean, I get why it looks the same on the surface, but the underlying mechanism is totally different.
How so?
When a visual scraper looks for that banner, it's taking a literal picture, an image buffer, and running optical recognition, or searching a 2D array of localized characters. It's guessing.
Ah, okay.
But the CLA uses that TNZS library to parse the raw telnet bytes. It maintains an absolute internal mathematical model of the host's memory state.
So it's not looking at a frame. It's querying its own internal database of the mainframe's buffer.
Precisely. And if you look closer at that same debug trace, it logs the exact parameters before it does anything. It's logging things like curl 16 and curcol 10.
Meaning it natively knows the exact cursor geometry.
Right. But the really huge one is that it logs keylock 0.
Oh, the keyboard lock state. Wow, that actually solves one of the biggest nightmares in legacy automation, doesn't it?
It absolutely does, because with visual scraping, you never actually know when the mainframe has finished loading a screen.
Right, so bots usually just have to guess. They use these arbitrary timer delays like, wait 3 seconds and just pray the screen is fully painted before I start typing.
And if the network is slow, it types into the void and crashes. But the keylock parameter fixes that.
Because the protocol literally tells it when to lock and unlock.
Exactly. The mainframe sends a specific byte sequence to lock the keyboard while it's thinking and another to unlock it. The CLA reads those state transitions directly from the wire.
So it doesn't hope the system is ready. It has mathematical proof.
Right. But getting to the point where it can actually read those transitions over a network, well, that's a whole other battle.
Oh man, the digital handshake. Honestly, the deep dive into the telnet networking was the most intense part of the logs for me.
It's a huge hurdle. Just getting a modern Python script to open a TCP socket and say hello to a 1980s mainframe framework is brutal.
And a lot of that friction comes from this thing called the Proxy 3270 gateway, right?
Yeah, Proxy 3270. It's everywhere in the hobbyist and educational mainframe world. People use it to expose emulators like Hercules to the public internet.
But it has this nasty quirk. It does these mid-session option renegotiations.
Which just absolutely shatters naive Python clients.
Well, because of how telnet works.
Right.
It uses in-band signaling.
Yeah.
The commands to manage the connection are mixed right in with the actual text data.
Exactly. Telnet uses this specific byte, the interpret as command byte, or IAC, which is hex F.
Right, FF. So when it sends FF, it's saying, hey, the next bytes are instructions, not text.
Right. So a basic Python script connects, gets through the first round of negotiations, and thinks, cool, we're in the data phase now.
Its internal state machine just totally stops expecting the rules to change.
And then Proxy 3270 suddenly throws a brand new IAC negotiation block into the stream.
And the naive script just panics. It throws an exception, deadlocks, or drops the connection because it doesn't know what to do.
Exactly. So to survive this, the creator built a custom telnet renegotiation shim directly into the tool.
Which is so clever. It basically intercepts the traffic before the Python logic even sees it.
Right. It acts as a shield.
Let's walk through the debug trace of this shim because it's wild. So the user types a command to list the available mainframes.
And the CLA spins up the shim, listening locally on port 127, port 0.0.1.
Then it connects upstream to a public reference installation, and the moment it connects, the server just starts aggressively firing negotiation bytes at it, demanding to know what kind of terminal it is.
Yeah, the server sends an IACD terminal type command. It's checking its ID at the door.
And the CLA actively spoofs its identity to manipulate the gateway. It doesn't say, I'm a Python script. It first responds by claiming to be an IBM dynamic terminal.
Which is a really strategic opening move.
Why dynamic specifically?
It tells the server, hey, I'm flexible. I can support multiple display modes. It forces the server to kind of reveal what it prefers to work with.
Ah, I see. And the server accepts that, but then pushes back and demands a more concrete specification.
Yeah.
And here's where the CLA upgrades its fake ID.
Right.
It fires back and says, actually, I am an IBM 3279-2E.
Which is such a specific flex. That string is basically a shibboleth in the mainframe world.
Right, because the 3279-2E was this super advanced color terminal, wasn't it?
Exactly. By claiming that identity, the CLA proves it supports extended attributes, color codes, highlighting specific grid geometries.
And that's what finally convinces the gateway to open the primary data connection.
But the shim is still doing work. The log shows it entering an intercept mode.
Yeah, the server sends a command refusing to use the end-of-record marker protocol.
And the shim just quietly absorbs that instruction, shields the fragile Python client, and smoothly replies, I won't use it either, to pacify the server.
All in milliseconds.
Oh.
And then the log literally says exit intercept. and the first actual payload byte arrives. The handshake is complete.
The shim is essentially a shock absorber, and once the connection is stable, the actual logic of the SLA takes over.
Right, so let's look at the actual live run from the user's perspective. The user types list backends, and the tool shows options like MVS 3.8 JTK5 and the VM370 system.
And for this test run, they target McGill CICS.
So the user invokes the skill. They skill colon music sign in usered equals $000 password equals music.
And the moment that executes, the SLA's structural awareness kicks in.
Right. It verifies it's at the Cerberus gate screen, figures out that MuseTSP is option 3, and constructs the payload.
It generates a tab command to move the cursor, inputs the character 3, and hits enter.
And because it has that mathematical grid we talked about, it knows exactly how many spaces that tab should move without having to ask the host.
Exactly. It updates its local state, fires the attention identifier key, and waits.
It waits for the data state to change. The bytes roll in. The MUSEFA CSP banner loads into its internal model, and the precondition resolves as true.
It mathematically knows it's at the authentication gate, so it injects the rest of the payload.
It inputs the user ID, $000, generates another tab to jump to the password field, types music, and hits enter again.
But here's the crucial part. It doesn't just print a success message and quit.
Right, the post-condition logic.
Yes, it forces the tool to wait and definitively verify the result.
So the mainframe processes the login, sends back the ADM and main menu, complete with a system clock reading 11:52 p.m., and the CLA parses that data state.
It matches the parameters against its required post conditions.
And finally prints a little checkmark in the log. Signed on as user 000.
It's a flawless execution sequence. No human operator touched a digital keyboard.
It's incredible. But I do want to talk about where this is currently limited, right? Because the developer's pretty open about the current boundaries.
Yeah, absolutely. Right now, the way you trigger these skills is pretty rigid.
Like you have to explicitly type skill : music sanyan, or use a very specific prompt-shaped wrapper like logon to music's ass.
Right. The routing is fixed. There's no active natural language processing engine yet to interpret really complex free-form intents.
So if you typed, check if I have any urgent system alerts and archive them, the CL can't break that down into a chain of separate skills.
Exactly. It is a highly capable execution engine, but it's currently waiting for a brain to do the planning.
But even just having this foundation completely changes how we think about the legacy problem, doesn't it?
Oh, fundamentally. Usually people look at 40-year-old IBM systems as technology graveyards.
Right. Fragile, isolated, totally inaccessible.
The SNA CLW 3270 proves that legacy is basically just an API problem.
Yes. If you have a translation layer that respects the old block mode protocols and manages the weird network states, you can integrate these opaque systems right into modern workflows.
And it's so scalable. The documentation notes that adding new capabilities, like teaching it to read a bank ledger or an airline routing table, it's just a text config change in the skills.ini file.
You don't have to touch the Python socket logic or the telnet shim at all.
Nope. You just write out the preconditions, keystrokes, and postconditions in plain text.
Which brings us to the roadmap. The developer mentioned that integrating an LLM-driven planner is the immediate next step.
Yeah, that's where this gets really interesting.
Right. An AI that can read your natural language prompt, look at the plain text skill catalog, and just dynamically chart its own route through the mainframe.
It's a fascinating trajectory for autonomous infrastructure.
It really is. And I want to leave you with a thought that kind of pushes this whole automation substrate concept to its absolute extreme.
Okay, lay it on me.
So we know the schools are just simple text blocks, right?
Right.
And soon, an advanced LLM will be able to parse the raw structural data of these mainframes. What happens when the AI doesn't just read the skills.ini file, but realizes it can dynamically write it?
Oh, wow.
Think about it. An AI agent gets connected to an undocumented 40-year-old government database it has never seen before.
It could just map the data state on the fly.
Exactly. It deduces the menu hierarchies, authors its own configuration file in memory, and just seamlessly starts executing complex workflows.
Without a human ever writing a single line of code for that specific machine.
Right. We're rapidly approaching a paradigm where the machine on our end isn't just talking to the ghost in the mainframe. It's actively teaching itself to master a forgotten language in real time, entirely on its own.
That is mind-blowing.
It really is. And that's our deep dive for today. Keep exploring, and we'll see you next time.